Okay, what chapters will be on the next exam? Chapter 7 and Chapter 8. Depends on how far we get through Chapter 8. All of Chapter 8.
Will you not be doing Chapter 9 then?
Chapter 9, let me see.
For the next exam.
Maybe the first part of Chapter 9. I don't think I'm going to quite get through it. Next exam is when?
Next Wednesday.
Yeah, next week. And so we have to start preparing for the next exam. So, for the last exam, a lot of people didn't do so well on the multiple choice. So let me spend a little bit of time talking about the multiple choice and see if we can. Okay. Like anything, the more practice you have, the better. In fact, there's certain things I wouldn't do without practicing. I couldn't imagine. And so, I remember, people going on training hikes for a big backpacking trip or something like that. The more you train, the better off you'll be. You don't want to go into these things cold. And that being the case, the more, multiple choice questions, and there are multiple choice test banks online. There's, I think, Quizlets and these other things. You can get a lot more practice with multiple choice. So if you find yourself not doing well on the multiple choice, maybe it's just lack of practice. That could be possible. If you find them tricky, then they can be very tricky. So let's take a look at these, like number 29. That's a chapter 7 problem. The total energy of 50 milliliters of water at 298 Kelvin is the sum of its potential and kinetic energies. Is that true or false? Do you think it's true? Or, how many of you don't know? It's true. Total energy is always, it doesn't matter what it is, it's the sum of the potential. 30. There are two types of closed systems, constant volume and constant pressure. Well, what is a closed system? Have you guys looked at the book? A lot of people never read the book. They don't even bother opening the book. But sometimes stuff comes from the book. Like this. I forgot to talk about this anyway. But there are three systems that are given here. Open system. Open system can exchange matter with the surroundings. So matter can leave, matter can enter. Energy can leave, energy can enter. So it can do both heat and work.
Yes. The top three couples open.
The closed system, they only show rigid closed system. This would be what we call constant volume. This is a rigid container. But the definition of closed system is that matter cannot escape. The only difference is matter can't leave or enter. But heat and work can leave and enter. But the thing is, you can make a closed system like this with a movable lid. So if the lid is not fixed, let's say we have a lid like this, then the lid can go up and down, But matter can't escape out or leak into the container. So this would be a closed system in which the volume can change. This would be a closed system in which it's rigid. Now, how do you know that? Well, it's hard. So these types of things, the more you see, the better off you'll be. If you take a look at the isolated system, can any matter escape out of the? No. Can any heat enter? If it were 100% insulated, then it would be a true isolated system. But most isolated systems, a little bit of heat can leak out, or some heat can leak in. Usually when you think about heat, you think about transfer of kinetic energy from hot, high kinetic energy to cold, low kinetic energy. And so if we know that a closed system can't exchange matter, we can have closed systems that are constant volume like the one shown, or we can have a closed system at constant pressure in which we have a lid in which matter can't escape. It's fully contained. And so actually this one is true. You can have a constant volume and a constant pressure closed
Very
system.
true. Would it not be false because constant pressure, it was as a bomb, would be considered an isolated system? Because little heat can escape so that we can perform through constant pressure. It's not a
The bomb,
perfect isolated.
yeah, the situation with the bomb is this. It's not an isolated, it's close to an isolated system. But with the bomb, let's take a look at the bomb. Why did it close?
I would say it's the fifth.
Okay. Here we are. When we look at the bomb here, this outer thing, we have a still bomb in here, but some heat can leak out of this bomb. And when we measure the heat capacity, we're measuring some of, including the heat leaking out to the surroundings. And so if it were purely isolated, this should be double-walled vacuum sealed. Nobody double walls and vacuums this. Whatever heat leaks out, leaks out. And we'll make temperature control the room so it stays consistent. It's but possible that, is this double-walled vacuum? It's possible that they could have it double-walled vacuum. Now that would be better. And then that would be an isolated system. But when you look at most bombs, they're not that. It's just expensive to have. And so let's take a look at a real bomb calendar, a picture of one of these. That looks pretty well insulated.
Those all look pretty expensive.
Yeah, 22,000, 25,000. These are well insulated. This is probably a good isolated system. 36,000. Pretty expensive. This is kind of the situation here, where it's not so well insulated. If you look at this one, this should go in the water reservoir. So it's either you could call isolated or closed system. For objects, Q is, what's the equation for Q? Amount times C times delta T, or amount times delta H, or amount times delta U, or both A and B?
Okay. Amount times C times delta T.
Yeah, A is correct.
Definition.
What's B?
B, amount times.
What is it? Amount times delta H equals what? And amount times delta U equals what? Well, yeah, delta U is a change in internal energy. And typically what we think of in terms of, let's say, amount times delta U is equal to what? Amount times delta U is going to give us an extensive amount of energy. And that extensive amount of energy gives the symbol what?
What is that?
But basically, Q is equal to all these. Q is equal to A, and Q is equal to B, right?
So technically it would be C, right?
Yeah, technically it should be C because Q is equal to all those. remember the equations? Q is equal to amount times C times delta D. Q is equal to amount times delta H. Q is equal to amount times delta U. So why isn't it A and B? These are the things you have to think about. You know, when you're doing this, you don't just want to memorize that, okay, it's A, it's the correct answer, but you have to think about all angles of the question, if possible, and then you'll be better off. And so why isn't it A and B? That's the question I'm asking is why isn't it A and B? Somebody tell me why. Mm-hmm. Hopefully this should be rapid.
It shouldn't be B because delta H and delta U already have Q in it.
No, Q is equal to the amount times delta H. Q is also equal to the amount times delta U.
Isn't delta U Q minus W?
Q plus W.
Q plus W. Yeah, delta H and
Technically we call it QP. I'm saying QB is the amount times delta V. Otherwise, delta U should be Q plus W. Right? You're right.
Maybe Q is used for different things.
It is. That's what I'm asking. This should be. You know, are you guys reviewing? You know, I think the most important, the number one thing you could do for the test is to review, you know, the notes, or if you don't take notes, review the book, you know, the chapter. I know a lot of people don't like to take notes, but I think notes are the biggest time saver because reading the chapter is so time consuming. Mm-hmm. But the next thing you should do is you should do all the problems that we did in class. Make sure you can do those without looking at how to solve them. And then the homework, and then the book, and then other sources. That's the way I would study. And so I was thinking should be easy because B should be
QB and QP.
well. There's something else. There's something else that's missing. And this is how do you see when something's missing? Well, you got to look at it over and over. When you look at your notes like daily, and not the night before the test, then you might notice something missing.
Is it because it's for objects?
Yeah. A is for objects. B is for
It's like chemical
reactions and processes. So that should have been a quick, easy answer. We know we have different equations for Q. An answer A, it's for objects, and answer B is for reactions and processes. And so that's what I mean by training. If you have a drill into your mind, then it's quick, it's easy. We don't have to worry about it. 33. A car interior. Well, 33 and 32 are kind of related. So 32, a mid-sized vehicle has over 3,000 liters of interior volume. How many moles of air is in 3,000 liters? Well, about how many liters is a mole of gas? 25. And so 3,000 divided by 25, what does that equal?
120, yeah.
122? 122 moles. Do you know about how much a mole of air weighs? Air consists mostly of
Yes.
empty space and what molecule? Nitrogen. How much does nitrogen weigh per mole?
14.2.
Well, nitrogen is diatomic, N2, so it'd be 28. And oxygen weighs 16 times 2 is 32. And And so the molar mass is going to be somewhere less than midway. Midway is 30, and it's more nitrogen, so it should be like in the 29, right? 29 grams. So we can figure out how many grams of air that is. Well, multiple choice is kind of nice because sometimes you don't have to do detailed calculations. We just do estimates. Especially if the numbers, when I see numbers like this, then I know there's no detailed calculation. The numbers are so spread apart. When I see numbers that are clumped close together, then I know I have to do a detailed calculation because, they're slightly off. And so for something like this, I'd never do a detailed calculation. I just estimate it, ballpark. And we can't because, on number 32, people were coming up to me and asking me, hey, I'm not given the temperature. I'm not given the pressure. I can't answer this question. But I was thinking, it doesn't have to be answered exactly, does it? "33. A car interior contains 3,600 grams of air at 40 degrees C and needs to be cooled to 25 degrees C. The specific heat of air in this range is 1.005 joules per gram degree C. And so Q, the air, is equal to what? Well, to cool an object, you have to add heat or remove heat? We have to remove heat. So B is out. And then it's either going to be A or C. A or C, do we have to do a really exact calculation for this? No. Not really. Not exactly. So how much is the temperature dropping?
15 degrees.
15, so it's going to be minus 15 times 36 times 1. So 15 times 36 is about what?
15 times 36?
54.
54?
Roughly 54.
Oh, there we go, 54.
Yes.
Because it's amount times C times delta T. It's an air is an object, and we use amount times C times delta T.
So it is.
C is about 1, so
Yeah.
okay.
I would say full answer is 54,270.
I got 5400, but 54 is fine.
That's good. Minus 54. 34. Bond calorimeters maintain constant pressure. Right?
A little small, but
False or true? False, right? This is false because if a gas is consumed, it might contain something at constant pressure, but it does not maintain constant pressure because if gas is formed, pressure is going to increase. If a gas is consumed, pressure is going to decrease. So the bomb has to handle increases and decreases in pressure. In other words, vacuums and high pressure. So that's false. Whereas, what's the other type of calorimeter? Coffee cup. Constant bomb. Coffee cup is, there are much fancier ones than coffee cups, but they're essentially the same thing. You just have an insulated container.
Motor show calorimeter.
Are there any other kinds of calorimeters?
Those are the two main ones.
Unless you want to use nice.
Those are the two main ones, and what's the main difference between the two?
Constant volume, constant pressure.
Constant volume, constant pressure. And so which one maintains constant pressure?
Well,
Not fun. Coffee cup. Is coffee cup, is that an open system, closed system, or isolated system?
closest.
more.
Because you can have a lid.
You can have a lid, but can matter escape out of the lid, like steam? If matter can't escape, then you're in trouble, because if the steam can't, let's say if you have a
And the
coffee
steam
cup,
can't escape, then it's not a constant pressure anymore. So it's
Right.
an open system. Yeah.
it's an open system. Right? It's got to be open, otherwise. Well, it could be a closed system, because we can have a closed system at constant pressure by having a movable lid.
Yeah.
But a coffee cup has holes here, and so matter can escape. So it would be more properly defined as a open system.
In the book, I don't know if this is right, but I think they said that both the bomb and the coffee cup were isolated systems. Maybe they were just talking about, like, theoretically they're
Um,
isolated systems.
Do you know where in the book it said that? I mean,
I can try and find it.
well, to answer your question, no, you wouldn't consider them isolated. You know, the bomb maybe, but the coffee cup definitely not, because the isolated system cannot exchange heat with the surroundings. And in fact, if you had a true isolated system, there would never be any heat escaping out of an isolated system. That could happen in the bomb because this bomb assembly can absorb all the heat of this system. That is the reaction that you're doing in there. But it can't happen with the coffee cup. $35. It's okay, Lily, if you find it.
I think I can find it. I know what chapter it's in.
Okay. Well, take a look at 35. 35 is what we did in the lab, kind of 50.0 milliliters of hot water.
Oh, I found it.
Okay.
Page 255. At the top.
Starting with this.
No, above it, it says we treat the system, the cup and its contents as an isolated system. No, on the other.
Okay. All right. I just need to see what they're talking about. Styrofoam. Styrofoam is a good heat insulator, so there's very little heat transfer between the cup and the surrounding air during the experiment. We treat the system, the cup and its contents, as an isolated system. Okay. This is why in the book they're ignoring the heat capacity of the calorimeter. And so in the homework problems for the book, they're saying that the cup does not absorb any heat. And the rest of the assembly does not absorb any heat. Here, isolated is mainly in terms of the types of things they're doing with. With a coffee cup, they're just doing reactions in which the volume doesn't change, and reactions or physical processes in which the volume doesn't change, like adding objects or something like that. And so what they're doing is they're making an assumption. They're assuming no heat is lost to this. Now, the other component of the isolated system is that no matter can be lost. And so if you restrict the types of things you do, you only look at certain types of reactions. And the types of reactions aren't going to generate a gas. So for example, if you're going to generate a gas here in a coffee cup, then do you think the coffee cup can handle it? That is, if we put calcium carbonate in here, and then add HCl, this is calcium carbonate solid, and then we add HCl aqueous, then what's going to happen is this is going to generate a whole bunch of CO2 gas. It generates the CO2 gas. One, it's not going to maintain constant pressure because eventually it's going to pop the lid off, even if this were completely sealed, airtight. In fact, this is what all the biochemists used to do. The biochemists used to have these little vials. This is sitting on the side. It's a screw cap vial like this. And they put their stuff. So it's a little test tube, plastic. And what they do is they put chunks of dry ice in here and then set it in the hallway. And then as people were walking by, all of a sudden there'd be a pop. and the little little rocket would shoot down the hall, and they were trying to scare people as some kind of practical joke. They're doing it all the time. So I was at the end of the hall, so I just hear these pop, 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 and a bunch of laughter. Anyway, so if there's a whole bunch of CO2 is generated here, it has nowhere to go. This is not an isolated system. A true isolated system is going to have no matter being exchanged. Not only that, if we have water evaporating here, it can evaporate out. So this is just extreme. They're just calling it isolated because the types of reactions that they look at, object plus object, the object's not going to come out of here. And so they're going to just treat it as isolated because there's no gas being generated or no gas being consumed at any of the processes that they're doing in a coffee cup. But we could have done this reaction in a coffee cup. I suppose if the CO2 is being generated here, we could also do this in a bomb, but it's not necessary to do this in a bomb because we could do this at constant pressure as well. So let's just say something for, if we start limiting things, then we can kind of picture it as an isolated system, but it's not a true isolated system.
So they're just like grossly.
Yeah, right. Grossly oversimplifying. What did anybody calculate the heat capacity of the calorimeter in experiment 2? It's a pretty small number. And so, okay, we're down, let's say it comes out to 10 joules per calorimeter per degree. Right? It's kind of a small number. And therefore, they say, well, 10 joules is close enough to 0, so we'll just call it 0. That's what they're doing here. They're just saying it's such a great insulator that we're going to call it 0. We're not going to lose any heat to it. And therefore, it's isolated. But in this particular problem, number 35, I don't make that assumption on the test. This is different than your homework. And so these are the things, this is why you got to go through the homework, you see how it's done, and some multiple choices, and then you go through the other problems to see how it's done. So you can get a better feel for things here. So 50 milliliters of hot water at 75 degrees C is in a cup. To this, 50 milliliters of room temperature water is added. Okay, if the cup did not leak any heat, or if the cup were a perfect insulator, if the cup had a heat capacity of 0, the heat capacity of 0 means no heat is absorbed by the cup, then this is no calculations required. You know what the temperature is going to be?
It's 2.2.
Well, it's going to be, no, this is not initial. It's going to be halfway between, what's room temperature?
25.
25. So what's halfway between 25 and 75? 50 degrees C. So if I'm taking 50 of hot and 50 of cold, then the temperature is going to be right in the center. But what's happening here is some heat is being leaked out because you can see it's not right in the center. Some heat is being lost to the what?
To the calorimeter, to the surrounding.
Yeah, to the surrounding. And so that means not only are we warming up the cold water, we're also warming up the
Calorimeter as well.
the calorimeter. And so let's see if I got numbers right. So we take 50 milliliters hot, add that to 50 milliliters cold plus the calorimeter or cup. We'll just call it the cup. And 50 milliliters.
At 75 degrees is what's inside the cup. We're adding room temperature water to it.
Yeah. Oops. Yeah, you're right.
Just have to flip it to 75.
So this is 25.0 degrees C. This is 75.0 degrees C. So the cup and the water are initially at 75.0 degrees C. The cup is not going to feel it because the inside of the cup is. The outside is going to feel a lot cooler, but that doesn't matter because the inside 75, so we call it 75. It's a heterogeneous temperature. So what do you want to call the system and what do you want to call the surroundings?
The system is the water surroundings is the cup.
Well, which water? We have two waters. Is all the water the system?
The system is the hot water.
System's hot water?
Yes, because we're working on it using the cold water.
Okay, if you say the system's hot water, then the cup also has to be part of that.
System.
Yeah.
So with the system that be cold water.
Probably easiest is to make the system the cold water. And that way the cold water takes heat from the surroundings. Well, the surrounding is going to take heat from the hot water and it's going to take heat from the cup because the inside of the cup is going to cool down, isn't it? Yeah. And so the easiest thing, we could say the system is the hot water, but we'd have to say, okay, the system is going to lose heat to the cold water, but it's not just the hot water, it's also the cup. It doesn't really matter. And so we just say Q of this is equal to minus Q of that. We don't really necessarily need to know what the system of surroundings are, but it doesn't know that. But it would be easier to do in this case because not only are we going to lose heat to the cup, but we're also going to lose heat to the air above it, and heat might leak out of the cup. We don't know. Is this a ceramic cup, or is it a styrofoam cup, or is it one of these vacuum? You know, these vacuum ones are pretty good,
It's a cup of cups, sir.
but not perfect, you know. And so, what do you do here? You say, okay, this is my Q of the system is going to equal the amount. Well, 50 milliliters is how many grams?
50 grams.
50 grams times C. C's not given here, but was given earlier, I think. Times delta T. So they give us the T final. The T final, this would be like a mixed temperature at 6 minutes. It's not the final temperature. Sometimes in experiment 2, we have the hot water, the cold water, and then the mix. Some people do this. They pick the final recorded temperature as T final or T mix. But that's not the case. We want to know what it would have been had we mixed it
In 6 minutes?
in less than a nanosecond. Yeah. It takes time to mix hot and cold water. It doesn't mix in a nanosecond, does it? But once it's completely mixed, and I said it's going to be completely mixed at around 8 minutes maybe. It should be completely mixed, then it'll normally cool down. So all we do is we know that cooling is exponential and we can just back extrapolate to what it should have been, right? At 6 minutes, had it been mixed in a nanosecond. I was debating whether I was going to make the experiment 2 the formal report or the sulfate. I'm just picking the sulfate. Now, in experiment 2, you talk about this kind of stuff, but it's all right. All right, so the amount that the cold water warmed up by is 50.0 grams times C. Does anybody have it memorized?
4.18.
4.18. We'll just go 3 sig figs. Joules per gram degrees C. And our delta T is going to be T final minus T initial. So T final is 52.2 degrees C minus T initial, which is 25.0 degrees C. Okay, so the cold water is going to warm up because this is going to be Q is going to be greater than 0, right? Yeah. If the cold water warms up? Who lost the heat?
This is the
The surrounding. And so this is equal to minus Q of the surrounding because the surroundings are going to lose heat, which means it's going to be negative. So to make a positive equal a negative, we have to multiply by negative. And so negative times negative. And so this is going to be negative. And which two things lost the heat? Well, the hot water and the hot cup. Okay, so Q of the hot water we can calculate. It's going to be the amount, which is which is how many grams?
50 grams.
50 grams times C, 4.18 joules per gram degrees C, times delta T. What's delta T for the hot water?
75.
T final, T final minus T initial.
75 minus 52.2. Wait, no, 52.2 minus 75.
52.2 degrees C minus 75 degrees C. So this is going to come out negative. And so that means we'll have a negative times negative to make these two things equal. Okay, and what's the equation for the cup? Okay, the amount, how many cups do we have?
We have 1 cup.
We have 1 cup. Did you weigh the cup? No. Okay. So we have 1 cup times C. What's the heat capacity of the cup?
X. We don't know.
Yeah, we don't know. So we'll just call it C of the cup. Times delta T of the cup. What's delta T of the cup?
Delta T of the water.
Yeah.
Water.
T final of the cup is going to be 52.2 degrees C, and then it was at the same temperature as the hot water, 75.0 degrees C. And then we solve for C of the cup. So if you're practicing, this is what you want to do. You want to do like triangles or whatever else. You want to do this problem. You want to do this problem so it becomes so easy that if this problem were given on the test, you'd be rejoicing because it's so easy. That's happened many times as a student, that I see a problem on the exam and I'm so happy because that problem I had drew down so much that it's simple. And so solve this, and the number should be, hopefully the number comes out positive and small, because hopefully the cup is decently insulated so we don't lose a lot of heat to the cup. But let's go ahead and calculate Q of the system over here, which is going to be 52.2 minus 25. Equals times 4.18. Oops. Times 50. 5684.8. Is that what you got, too?
Give me a moment.
5684.8 joules has to be gained by the cold water. Minus, let's calculate the two terms here. Do you have the first term?
Yeah, Q of the hot water should be negative 4765.2.
Okay, thanks. Minus or plus? Minus or plus?
It should be minus, but you could keep, no, it's just minus.
It's going to be plus C of the calorimeter times, what's the delta T?
Negative 22.8.
Negative 22.8. Thanks.
I just combined them for negative 22.8 C calorimeter.
Okay, so let's solve for the C of the calorimeter. What does C of the calorimeter equal?
Negative 4788.
Negative 47 point.
Negative 4788, no points.
Okay.
Because the 0.2 and the 0.8 combined for a 0.0, I guess.
All right, now, what are the units here you got?
Oh. Joules per C. Yeah, joules per
Joules per degree C. All right. Now there's one problem with that heat capacity.
It's 4,788.
Is it 4,788? That big?
Yeah, 4,788 joules is what I got.
There's two problems with this. One, that's a lot of heat. That's a huge amount of heat. That means that it's sucking. But the problem is it's not sucking because it's negative. Negative means the heat is not being absorbed by the cup. It's being expelled by the cup, which means that's great because if the cup expels heat, then it can keep your coffee warm or your water warm. And in fact, you could heat up your water with the cup. You just put the water into the cup and it's going to expel heat.
I can make a patent for that.
Yeah, you should make a patent for that. You could, those perpetual motion machines on. Yeah. This would be the equivalent. So is something wrong? One thing is. One thing that's wrong is it can't be negative. If it's negative, there's a problem. And it shouldn't be this huge, because if it's this huge, that's another problem, because the cups aren't supposed to be absorbing this much heat. So this means if this were positive, that means your coffee is going to get instantly cold. You pour it in there, or whatever, hot tea or whatever you're drinking, because the cup is going to absorb so much of the heat. So is it negative? Is it correct? No. It should be positive. And here, I mean, if we just say it's negative and distributed it, it's going to be positive. It shouldn't be positive, so this is going to be positive. The next thing is, what's going on with the energy? It's too big. We expect it to be small. For example, styrofoam, the book is assuming is 0. 0 joules are lost for every degree C change. So if the styrofoam cup warmed up by 100 degrees C, how many joules of heat? 0 joules of heat to warm up the cup. So redo it, because this is negative times a negative. And so redo that. And so there's certain things you could do if you know some of the numbers. And so you know some of the numbers because you've practiced and you've done other problems to see, although there aren't enough heat capacity and cup problems in this. And so what does it come out to? 5684.8 minus.
I got like 40.3.
40.3? Okay. Anybody else? That sounds right. It's kind of typical. So this is typical. From experiment 2, you're going to see something like that. 10 to, depending on how well sealed everything was, 10 joules to tens of joules per degree C. This one's a little high because this might be a ceramic mud or something. That's number 35. And then number 36. So why don't you take a look at 36? I'm going to move on since I don't want to spend the whole time with this here. And now I just posted exam 3 here. So why don't you go through the multiple choice on exam 3 and we'll talk, at least read them, and then we'll talk about them. So this is on. And if you really want to improve multiple choice, then take a look at some of the multiple choice test banks that they have for thermo. Other things. Okay, so that's exam 3. I need to continue with chapter 8, otherwise this exam's only on one chapter. But, I would do this problem like this, and then what I do is I would just think about the strategy that was used. Why this says Q the system? Why not that? And those types of things so I can better remember it. And the reviewing thing is important because otherwise it's hard to remember this kind of stuff. So chapter 8 deals with matter interacting with light. If something's black, what does that mean?
It's absorbing all visible light.
Yeah. Have you seen these ultra black objects?
It, I haven't named, but yes, I have.
Is it ultra black or what they call it?
Vent? Oh, vent. Vent black.
Vanta black?
I remember Vent black 3.
Isn't there drama with like an artist
Yeah,
or something like that?
Someone like claimed that it was there,
Yeah,
and
they-
no one else could use it.
And then someone else made like a new one, and it was like that person was the person that could use it.
Oh yeah. Vanta black. So you guys you've already seen this, right?
Yeah.
Yeah, when it absorbs the visible light, it's hard to see. Do you know, there's some deep sea creature, have you seen that? With the blackest skin ever found.
You mean the viperfish?
Is it viperfish? I don't remember. I didn't like videos. I have it. It's in this TV. Deep sea fish. It's like one of these things. And the skin is so black. They measured it. Pretty impressive. But anyway, light interacting with matter. Well, let's continue with that. So we expect things to be like a hydrogen lamp should be what we call a black body emitter. What's a black body emitter?
Something that will produce emit already light.
Yeah. All colors of the rainbow. But the hydrogen wasn't the black body emitter. No, it turned out to only emit certain colors of light. And those colors correspond to allowed energies for the electron. Not only that, there was something called the UV catastrophe. Just roughly, what was the UV catastrophe?
Doesn't that have something to do with quantum physics?
It was the drop in radiation that was observed in the UV range where it should have been an increase. And so the hypothesis was that the electron can only have a certain allowed energies. And so the first one is the Bohr model or the Bohr hypothesis. And they called this, there was some acceptance for this. Normally a hypothesis is a tentative explanation and a theory is a what? Widely accepted. And so Bohr had some wide acceptance, but there was a lot of trouble with it. And so the Bohr theory or hypothesis. And for Bohr, the electrons have allowed orbits and forbidden orbits. Each orbit corresponds to an energy. And so when we look at the hydrogen atom, the electron, the first allowed one, let's say, is here. The next allowed one is out here. The first orbit is called the n equals 1 orbit. The second orbit is called the n equals 2 orbit. And then the next allowed one will be the n equals 3. But the situation is everything in between those is going to be forbidden. And so this purple region is all forbidden. And what happens with these orbits is they don't go or increase linearly. They increase like this. So the n equals 4 is way out here. So these orbits get further and further spaced apart. Do you know what the last allowed orbit is? N equals infinity. And so how many allowed orbits are there in the Bohr model? Infinite. And how many forbidden orbits are there in the Bohr? Infinite. And so it's weird. There's an infinite number of forbidden orbits, and there's an infinite number of allowed. And the forbidden orbits are actually greater. There are more forbidden orbits than there are allowed. So you can't go to 2.1 or 2.11 or anything in between. And so what we say is that energy is quantized. You know, this is quantization of energy. Rather than what? If it's not quantized, then we say it's continuous. Black bodies should be continuous. They shouldn't be quantized like this. So what's the proof of this? The proof is what, the experimental observations show. The experimental observations show that not all energies are allowed. But, in a proper theory, we should have a fundamental picture of what's going on. So what is the fundamental picture? What's causing the electron not to orbit anywhere in between 1 and 2? N equals 0 is not allowed. What's the proof? Well, this is just taken without proof. And so it's a postulate. This is one of the postulates of quantum mechanics, at least the Bohr theory. It's a postulate that we only have these allowed orbits. Now the math comes in. The math is, we call this first orbit R1. This is the radius for the first orbit, R1. From the math for this, for the H atom, R1 is equal to 0.54 angstroms. And then we see a pattern in the orbits. And so the radius of the orbit is equal to n squared R1. Sometimes they call it R0. No, I'm just going to call it R1. 0 is not allowed. The R0 would be the original. Sometimes they call it A0. There are lots of different symbols. So it could be R, A, whatever symbol they want. This is our book called. Well, anyway, so this would be 1 R1, or just R1. What would this be? This one would be 4 times R1. This one would be 9 times R1. This one would be
16 times R1.
16 times R1. And so these are the orbits. The orbits are going to expand out this way. And so the orbits do this divergence. But the energies are, oddly enough, the energies can be calculated just from physics. This is just, basically this is classical physics with the restriction that not all the energies are allowed. The energies are going to be quantized. For the energies, we map them out. The energies converge. here. And so the lowest energy orbit is going to be an electron in R1. And so the energy for this orbit is equal to E1. E1 is equal to,
One electron.
it's equal to, okay, this is the base energy, which we call R sub H, divided by N squared. This is for the H atom. R sub H divided by N squared. Where R sub H is this number that we have, which is minus 2.1718 times 10 to the minus 19 joules, something like that. You don't have to memorize R sub H. Oh, if you want to memorize it, go ahead and memorize it. No problem.
So for each atom at R1, there's only one electron per right?
Yeah, there's only one electron in the H atom. This is where R sub H is equal to negative 2.179 times 10 to the minus 18 joules. That's R sub H. And so E1 is just going to be negative 2.179 times 10 to the minus 18 joules. What's E2 going to be? E2 is going to be a jump up in energy, and E2 is going to equal minus, what is it? R sub H, sorry, it's minus R sub H, and R sub H we'll call it positive. Rather than negative. It doesn't quite matter. We're going to change the equation. But this is going to be equal to minus R sub H over,
Actually, it would be N squared R1.
yeah, N squared, and N is equal to 2. So this is going to be minus R sub H over 4. And then E3 is going to be equal to minus R sub H over 9. And then E4 will be equal to minus R sub H over 16. And so what happens is these start to converge. That is, they start to get closer and closer to one another. And then eventually we're going to get to E infinity. E infinity is equal to minus R sub H over infinity squared, which is going to approach what? Well, whenever you divide by infinity, it approaches, non-infinity approaches 0. So E infinity is equal to 0. So the highest energy is 0 joules. The lowest energy is minus 2.179. Minus 2.179 times 10 to the minus 18 joules. So the way we visualize this is like this. This is something that we call a potential well. And the way it's visualized is like this. If the electron were in the highest energy state, E infinity, then how far from the nucleus would that electron be?
Infinitely away.
Well, it would be N squared R, which is infinity squared R. How far away is that? How far away is infinity squared?
Infinity away.
Yeah, it'd be infinitely far away, which means
It's not anywhere close.
it's no longer attached to the nucleus, right? And so what that means is the electron's completely ionized. If an electron goes to the n equals infinity, it's gone. It's no longer part of the atom. And so that means if an electron's infinitely far away, it's no longer a part of the atom, so it's not going to interact with it, and its energy should be 0. So the energy is not absolute. This is not the total energy. This is a relative energy. A relative energy meaning that the electron separated completely from the atom is going to have zero energy. Does it really have zero energy? No, because the total energy of electron is the sum of its potential and kinetic energy. But relative to an electron in an atom, it's going to be zero. So this is going to be zero energy here. We'll call this zero. As the electron moves closer to the nucleus, what's going to happen? It's going to be attracted because unlike charges attract. So the negative charge on the electron is going to be attracted to the positive charge on the nucleus. And so what's going to happen is the energy, as the electron gets closer and closer, the energy should drop until we hit the minimum energy. And what is the minimum energy? That is,
179.
yeah, this is as low as it's going to get. That is negative 2.179 times 10 to the minus 18 joules. So how much energy does it take to knock an electron off the hydrogen atom?
Or infinite, I guess.
Not infinite. How much energy does it take to knock out an electron off a hydrogen atom? That is, we have to climb out of this.
It would be R sub H 2.179 times 10 to the 18th joules.
Yes. Okay. I mean, i.e., the ionization energy, you're right, R sub H would be it. The ionization energy is going to be plus 2.179 times 10 to the minus 18 joules per H atom. That's how much energy it takes to ionize hydrogen. How much energy does it take to ionize a mole of hydrogen?
Well, let's see here. We're going to take R sub H and multiply it by, oh my God, what is
Yes. And so let's get it in terms of kilojoules per mole.
let's see, that one.
I'm going to write an arrow here for this because energy is not continuous for the H atom. It's going to jump, jump, jump. This is just the trend.
This is going to be positive, right? 1,312 kilojoules. So I got,
1,312 kilojoules
yes,
per mole of H atoms.
per mole.
Okay.
I think that's right.
It sounds about right.
Question.
Mm-hmm.
For your IE, you put 2.179 times 10 kilojoules.
2.179 times 10 to the minus 18 joules.
Oh, I thought that was a K.
Right. It's times 10 to the minus 18 joules. What are you more familiar with? Joules per atom or kilojoules per mole?
Kilojoules per mole.
Kilojoules per mole. And so what we're going to do is this. What kind of light will ionize hydrogen? And so there are different ways we could do this, right? But one of the ways we could do this is we could look at visible light. So visible light ranges from 760 nanometers to 390 nanometers. 760 nanometer light is red light. How many kilojoules per mole of red photons do we have here? And so let's go ahead and do that. The energy of the light, energy of the photon, is equal to h nu, which is equal, you don't have to have these memorized, except for maybe this, the relationship between u, c, and lambda, which is equal to hc over lambda. Okay, lambda should be in meters, so this is going to be hc over, okay, 760 nanometers is 760 times 10 to the, nano is what? Negative 9 meters. And so let's go ahead and calculate. H is 6.626 times 10 to the minus 34. 6.626 times 10 to the negative 34. C is 2.998 times 10 to the 8 equals, divided by 760 times 10 to the negative 9 meters. And this gives me the wrong answer I have here. Let me try that one more time. (6.626) times 10 to the negative 34 times C 2.998 times 10 to the 8 divided by 760 times 10 to the negative 9.
Negative 9. For 760 times 10 to the negative 9.
Nanometers. Yeah. What did you guys get?
2.6137 times 10 to the negative 19.
Yeah, okay. So we got 2.61, well, I got 2.6138 times 10 to the negative 19 joules per photon. Remember, because this is the energy of the photon, which means how many joules per mole of photons? So how could you calculate that?
Multiplied by Avogadro.
Yes. And then we're going to get what?
Uh, 157,000.
157,000 joules, or 157.4 kilojoules per mole. So red photons have an energy of 157.4 kilojoules per mole. The ionization energy of hydrogen is 1,312. Is red photon going to be enough? No. How many kilojoules per mole for violet photon at 390? So it's going to be HC divided by 390 instead. So I can convert it quickly. Maybe multiply by 390 divided by 760. So multiply by 390 divided by 7. Unless you already have it.
5.093 times 10 to the negative 19. Or yeah, the first one's for joules per photon, or 306.7 kilojoules per mole photon.
306.7. Is that what you got? 306.7 kilojoules per mole. Is that enough?
No.
No. We're going to need higher energy.
A lot higher.
Probably UV or maybe
X-ray.
X-ray.
God forbid we need to go.
But sometimes, so we try to visualize things in different ways, like visible light. We can visualize in terms of wavelength, we can visualize in terms of frequency, although people don't really do frequency for visible light. We could do it in joules per photon, or we could do it in kilojoules per mole of photons, etc. There's a lot of variability. So at least we know visible light. And then we can try some of the other types of light. And UV, it's most likely UV. UV is going to go over, we need 3 times, or actually more than that. We need about 4 times the energy, over 4 times, right? UV goes over several magnitudes, orders of magnitude. And so 10 times would be an order of magnitude. And so I already know what type of light it's going to be. What type of light it's going to be? UV. UV. Yeah. It's not going to be X-ray. All right. So this was pretty successful because the lines in the hydrogen spectrum were due to electrons being excited and then dropping in energy. So So for example, the red line in the spectrum comes from an electron being excited to the third energy level and dropping down. So this is an electron transition. So electron gets excited to the third energy level here, and then drops back down to the second, and then emits a red photon. Eventually it'll drop back down to the first, but if it drops back down to the first, it doesn't emit a red photon. Do you know what it emits?
It's so much more.
Well, this is tricky because this is a bigger energy drop. And so that means it has to have higher energy than.
Could it be either violet or UV?
It could be a higher energy visible, but it turns out it's UV.
Let's say cosmoviolet UV.
And so we don't see it. The green photon is a result of dropping from the third floor to the second floor. That would be the green photon. Green, try it out. This just came from calculation. The blue photon comes from dropping from the fourth floor to the second floor. And the violet photon comes from dropping from the, what is this, third, fourth, would not be fifth, sorry. And the violet comes from the sixth floor to the second. What if we went from the fourth floor to the third floor? If we drop from the fourth floor to the third floor, that's smaller energy than red, which is probably going to be in the infrared. And so there are additional drops here, but you can't see them because they're going to be in the infrared or the ultraviolet.
Would the drop from floor 4 to 3 be a similar red? Was it similar amplitude to red or orange? Would it be greater?
4 to 3 is infrared.
Is it also infrared?
Is also infrared. We don't see those. And so we can calculate the energy of these. Let's go ahead and calculate energies because we know the energies of the state. And so this is it here. The visible lines here are called the Balmer series because Balmer is the one who discovered these. The ultraviolet lines were discovered by, wait for it, here, Lyman. And so Lyman discovered the ultraviolet lines here that drop all the way to the first floor, which are big drops. And then one other person discovered the infrared one. That one other person is not discussed here, I guess. So I guess we don't have to worry about that. But there's one more series. And so the Balmer series, you don't have to memorize this at all. Let's go ahead and calculate the energies here for these transitions. So we just calculate delta E. We know what the energies are. Delta E is equal to E final minus E initial. So delta E equals E final minus E initial. E final is going to equal E sub n final minus E sub n initial. E sub n final is going to be minus R sub h over n final squared.
Yeah.
Right. Minus E initial will be minus R sub h over n initial squared. Those are the energies from physics here. And then we factor out the R sub h. And so what we get is delta E for this is going to equal minus R sub h over 1 over n final squared minus 1 over n initial squared. This is equal to E the photon that has to be emitted. So that's the energy per photon. And then this equation is given a name. This equation is called the Rydberg equation. Now, the Bohr model has been abandoned. You know, this Bohr theory. Theory should have widespread acceptance. So maybe it got widespread acceptance and then everybody jumped off the boat. Everybody jumped off the boat because the Bohr theory couldn't explain anything with more than one electron. Not all parts of it were dropped. And so the Bohr model theory is no longer widely accepted. In fact, no longer accepted at all. We'll just say used. But the Rydberg equation is still valid. There are two ways that the Rydberg equation can be derived. One is by the energies. There's an energy pattern here. And the energy pattern here can be explained by this. So the Rydberg equation can also be derived empirically. This was derived from physics because the physicists figured out what the energies of those orbits are. But we could have also derived this empirically by just looking at the patterns. Leave it at that. It's still valid for the H atom. And single electron species. For single electron species, we have to modify the energy of the orbit. The energy of the orbit, E sub m, is equal to Z times R sub h over n squared. So we have this Z term in here. It was negative. And so our delta E is going to have a Z term in there as well. Z squared. Z squared, sorry. It has to be modified, so Z squared. And so delta E, the Rydberg equation is modified. It's going to be minus Z squared R sub H 1 over N final squared minus 1 over N initial squared. So certain things are carried over from the Bohr model. One is quantization of energy. Another is this Rydberg equation for the H atom and the Rydberg equation for the one electron species. And the reason that's carried over is because this is some mathematical pattern that can be derived empirically as well as from the physics. And so those are carried over into the new model. And so the present day model, what is the present day model called? I.e. theory. Called the quantum theory or quantum mechanical model. So let's take a look at the quantum mechanical model of the H atom.
Those are 3 minutes. 3 minutes.
3 minutes. The energy, this is called an energy level diagram, and to be more specific, we call it an atomic energy level diagram. Looks very similar here. That is, in the atomic energy level diagram for the quantum mechanical model of hydrogen, we have allowed and forbidden. The first allowed energy is E1 here. The next allowed energy is E2, etc. It looks exactly the same. However, these allowed energies don't correspond to orbits. They correspond to orbits. And so overall picture kind of looks similar. But on closer inspection, what we see is this. E1 is down here. And the first allowed energy we call 1s, or 100. 100 is the number code for NLM, which we'll talk about. Those are the quantum numbers, or we call it 1s. All right, the next allowed energy is a bit trickier because in the next allowed energy, E2, we're going to have the 2s, or the 200. And for the hydrogen atom, there's some more. There are 3 more sublevels here. Actually, not sublevels, I shouldn't call it that. We also have something called the 2p. The 2p is a sublevel. And within the 2p sublevel, we have individual allowed ones, which would be the 2, 1, negative 1, 2, 1, 0, 2, 1, 1. So we end up with some kind of pattern like this. And each of these is called an orbital. And an orbital is allowed energy, the electron. And so when we promote the electron up here, there are 4 possible orbitals that it can occupy, and all 4 of these have the same energy. The next allowed one will be E3. In E3, we have the 3s here that's allowed, and then 3 3p's, and then 5 3d's. And the way we label this is we label this one 300, and then we'll have this one will be a 3 1 negative 1, 3 1 0, 3 1 1. And then over here, these are what we call 3 2s. 3 2, negative 2, 3 2, negative 1, 3 2 0, 3 2 1, 3 2 2. And so at the first energy level, we have 1 orbital. In the second energy level, how many orbitals do we have? 4. We have 4 orbitals. They're all the same energy for hydrogen atom and 1 electron species. In the third energy level, how many possible orbitals do we have?
9.
9. Do you see a pattern?
I do.
What's the mathematical pattern?
Exponential.
N squared. So this is equal to n squared, or 1 squared. This is equal to n squared, which is 2 squared, which is 4. This one's going to equal,
3 squared.
yeah, 3 squared.
And 9.
Yeah. And so when we get to equals E4, how many orbitals are there going to be?
16.
16. So let's go ahead and write them out.
Do we have enough time?
No, we don't have enough time.
We'll do it next time. And then we're going to talk about the finer details of this next time too. So why don't you take a look at the old exam 3 I posted, and we'll talk about that on Thursday.